Why are we interested in threads? Well, this is sort of a fairly canonical argument. Future processor performance enhancements, as we all know, are likely to come from multi-core processors. It's going to come from having parallel machines rather than enhancing single-core performance. Often, though clearly not in all cases, especially around here, programmability is a limiting factor. There is, in fact, lots of research on alternate programming models for multi-core processors or parallel machines in general. There are many people working on transactional memory. There's a lot of interest in message passing models, clearly. There's also interest in more flexible data parallel models that we could use to program these machines. On the other hand, if we're talking about parallelizing a single non-numerical application, I think if we look at the status quo, at least, pretty clearly threads and locks actually dominate, particularly if you look at what's going on desktops. The main reason that they do, I suspect, is essentially because they're there. Threads and locks have been around for a long time. They clearly predate the widespread use of multi-core processors. They were there primarily to deal with multiple event streams and things like that that had nothing to do with parallel machines. They were originally used primarily as a programming model for other reasons, but that makes them widely available and the natural mechanism to exploit. On the other hand, if we look at threads and locks, in general, in many circles at least, they have a bad reputation. Certainly, we all have horror stories about intermittent failures of multi-threaded applications. There's a general feeling that they're too complicated. We commonly hear statements like locks don't compose, which I think is somewhat true, though it's actually hard to make that precise. If you do a web search for the phrase "threads are evil," you get lots of hits. So the point of this talk really is that not so much that these problems aren't real at all. I think some of these problems are real, and we should be looking at alternate programming models as well. On the other hand, not all of the bad reputation here is inherently deserved. Not all of it is really rooted in profound problems. Sometimes the issue, I'll argue, is just that we got things wrong the first time, and we haven't gone back and fixed some of these things. Up until now, a lot of this wasn't all that important because parallel machines were basically multiprocessor machines were relatively esoteric. Most people didn't deal with them. On the other hand, now that's clearly changed. And in fact, I think it's important to fix these problems because now they have become important, and I'll try to convince you that most of these problems, in fact, are fixable. The problems aren't really inherent. I'm going to be a little bit sloppy here about what's actually my work and other people's work here. There were many contributors to a lot of this. There's a partial list up here. Last time I checked, 2 of the people up there actually work for Google. That may have changed by now. It's hard to keep track. But so there are many other people who worked on this. As always, when looking back, it's easy to complain about stuff that was done in the past. In fact, I don't know if I'll get this across here. Some of what was done in the past is, in fact, quite clever. And it's quite clever, but it didn't quite make it. It's a very interesting near miss, in my opinion. So it's very easy to take cheap shots at stuff that was done 10 or 15 years ago here, and I apologize for that. But nonetheless, I think these are things that need to be corrected. Some of the solutions here, some of these problems actually are difficult technical problems. Some of them are not. So some of the solutions I'll point to here are, in fact, quite obvious when you look at it. And in some sense, that's part of the point. We, in some cases, even got things wrong that are, in fact, I think, not that profound. So as a group, what we've been doing here is basically trying to identify some of the problems that we have with multi-threaded programs at the moment, and trying to resolve those whenever that's possible. There are a number of things we've been trying to do. Some of the technical solutions, in fact, turn out to be non-trivial, and I'll try to give some hint of that at least here. So working on the technical problems has certainly been part of this effort. there's also been an effort to try to push some of this through the C++ standards committee. Lawrence Crowell, he was in the room, he has been heavily involved with that as well. So the plan here is the goal here is to provide proper support for threads in the next C++ standard, which is for historical reasons, well, maybe historical reasons, not quite clear yet, is referred to as C++ 0x. The joke here for a long time was that x may actually be 0xa. The status of this as of the moment is that the current working paper for the next C++ standard actually includes a lot of what I'm going to be talking about, but not everything. So it includes the threads memory model that I'll be touching on here, which basically defines what it means to access a shared variable from a thread, which is sort of the foundational question that we're addressing here. It also includes, with thanks in large part to Lawrence, an atomic types and operations library in the current draft. And it almost includes a threads API as part of the language definition as opposed to the definition of an auxiliary library that you use in order to get threads. We're trying to do some other things as well here. In addition to the C++ committee, several of us have been talking to the C and POSIX committees. Currently, at least my understanding is that the C committee is fairly likely to do things in a way that's similar to what the C++ committee is doing, which would be a very good thing. We've also, several of us have been spending time talking to other interested parties, and the other interested parties, it turns out here, are mostly processor vendors in order to address some of the other issues. In particular, the issues here, as I'll show you, extend down to the hardware level in a few cases. So one of the things that's actually improved dramatically recently from my perspective is that both Intel and AMD have released new memory model specifications for what's commonly known as the x86 architecture, which resolves some of the issues that I'll tell you about later here. And we've been trying to sort of spread the word about some of these issues to try to resolve past misconceptions. The rest of the talk here is basically structured as a list of problems and then explanations of the solutions that we expect to use in order to resolve those problems. Most of these, in fact, are now in the C++ 0x working paper. But I should warn you, they're not yet in a formal standard, so anything can still change at this point. Again, the main goal here is try to convince you that, first of all, there are problems here. On the other hand, these problems are solvable, and there's a solution. For the most part, there's solutions on the way. So starting with the list of problems here that we encountered, I actually want to start down sort of at the lowest level, at the hardware level. If we're talking about multi-threaded programs, basically everything relies on what it means to assign to a shared variable and to access the value of a shared variable. That basically gets us to this issue of memory consistency or memory ordering, which is underlying most of this. In order to get you a better feeling for what we're talking about here, if you're not familiar with the issue, I'll sort of give you one simple example. If we have two threads, one of which assigns to x and the other one assigns to y, both of which are shared variables, and then each thread reads the other variable. The question is, can both of these threads see the initial value of the variable, fail to see the assignment in the other thread? With most people's intuition of how threads work, that shouldn't be possible because one of these threads has to go first intuitively. Thus, one of the assignments of 1 has to go first, and therefore the other thread should be able to see a 1. There are, in fact, some basic algorithms that rely on the fact that this can't happen. And a lot of programmers, when they first start to program with threads, basically assume that this is the case. They implicitly assume what's normally called sequential consistency, which you can informally define as the threads behave as though the steps of the individual threads are just interleaved. So by people's normal intuition, this outcome here should not be allowed. Whether or not this is allowed, in fact, is determined by all sorts of things, including the hardware, the compiler, and thread libraries, and so on. Basically, since everything is built on top of the hardware, for all of these things to do their job correctly, to sort of provide the right semantics here, we need to get the understanding of the hardware right. The interesting observation here is that if we look at this particular outcome, most hardware, in fact, even if you assume that the other layers of the stack, in fact, translate this directly to hardware instructions the way you expect, most hardware will, in fact, allow this outcome here. Most hardware will, in fact, allow both of those to read 0. The reason for that is that most hardware, when it executes a store instruction, in fact, does not make the results of that store instruction immediately visible to other processors. It just goes into a write buffer in the processor where it's not visible. So if these execute basically exactly in lockstep, then the initial store may not actually have made it to visible memory yet, or to coherent cache by the time the second statements are executed. So both of them may, in fact, see the initial value. So what happens here? Well, fundamentally, the fact that the hardware doesn't quite implement what we expect to see shouldn't be a problem, because we have that in all sorts of other respects as well. We normally just try to hide any sort of misfeatures like that in the software higher up in the stack, right? So provided we actually understand the hardware rules, we should be able to exploit those hardware rules to implement some usable programming model that we can all agree on, and that we can then program to, and that can be implemented reasonably on the hardware, possibly by telling the hardware something else. Widely held beliefs, at least as far as I can tell about this, are that in general, allowing the hardware to cheat like this and give unexpected results is probably a good thing. Because what happens is that most of the time we actually don't care about simultaneous accesses to shared variables like that. As you'll see, we generally try to discourage people from introducing simultaneous accesses like that anyway. And most of the time we don't care, and since we don't care, the hardware should be allowed to do whatever is cheaper, which includes giving us these unexpected outcomes. Occasionally, we will care about outcomes, about disallowing things like the outcome on the last slide. In that case, what we do is we provide, and hardware generally provides, other instructions that allow us to notify the hardware that we do care about the memory visibility ordering. These are normally called memory fence instructions. On most hardware, they take that form in any case. That allow us to get back to sequential consistency, to the behavior that programmers expect. So in those cases, basically, the software stack can hide the fact that the hardware will reorder these memory accesses underneath the covers. So that's the theory. So what actually happened? Well, if we go, as I said, recently things have gotten better here, fortunately. On the other hand, if we go back to sometime around 2006, in fact, if we looked at many of the architectures, what actually happened was that not only did they have somewhat weaker memory ordering, not only did they allow this kind of weaker memory ordering, they often didn't specify very carefully in ways that some of us could understand exactly what reordering was allowed, what the semantics were, and what they weren't. This was shared between several architectures at the time in any case. The result of this, as far as I can tell, was general confusion, and sort of some weird things happened higher up in the software stack, which probably sort of tended to aggravate the issue, because it also made it less clear to the hardware designers what was really expected of them. So I put up a couple of interesting consequences here that we found in this process. I guess GCC is commonly used here. So if you look at what the GCC compiler provides, it actually exports a primitive directly to the programmer that allows you to control this sort of memory reordering. It basically has a call called underscore synchronize, which is intended to ensure that memory operations are not reordered across this call. So it's defined in the documentation as a full memory barrier. On the other hand, if you look at its implementation on x86, it actually, at least last time I checked, actually generates a no-op, which it turns out by no reasonable interpretation of the x86 memory model is actually what it should do and be consistent with that specification. And the problem is, as we'll see from the next slide, I'll hint at on the next slide, it's actually not clear that this is fixable. Just fixing the implementation here probably won't solve the problem for performance reasons. Another interesting consequence or another interesting situation that at least to me seems strange, and I have never gotten sort of complete explanation of this from Intel or AMD engineers, is that around the time of the Pentium 4, the architecture introduced something called L-fence and S-fence, load fence and store fence instructions. On the other hand, based on the understanding of the x86 memory model that most of us had, but which wasn't clear from the description at the time, loads and stores on x86, in fact, are ordered anyway. So it's not at all clear what these do. So as far as I can tell, for most code, L-fence and S-fence on Pentium 4s are, in fact, something like 100-cycle no-ops. This is not completely true, actually, but so there are some funny corner cases where you might actually need this, which makes this more interesting. If we look at the performance assumptions that went into this, the assumption here was that by limiting memory ordering to explicit fence instructions, we only required the hardware to enforce ordering of loads and stores precisely in those cases where we needed it, so we should always be ahead. In fact, that's also not the way it worked out as far as I can tell. So if we look at the performance of these instructions, and I'm sort of picking on a slightly obsolete chip here, which was probably the worst offender in some ways. For Pentium 4, the cost of one of these instructions that actually enforced ordering was in general on the order of 100 cycles. In the best case, that's assuming no cache misses and so on. So that's kind of expensive. On the other hand, if I compare that to, as far as I know, around that time, there was really only one architecture that really enforced sequential consistency at the hardware level, and that was PA-RISC. PA-RISC, in fact, was reasonably performance competitive, which suggests to me that certainly it did not cost 100 cycles per memory operation in order to enforce ordering on a PA-RISC processor. So in fact, the theory here doesn't seem to have quite meshed with reality either. The other interesting thing that happened is that we ended up with some memory models in which it was actually not at all clear that the fence instructions that were provided by the hardware actually could be used to get you back to full sequential consistency. And hence, if in fact this was not, if full sequential consistency is not implementable, it turns out you also can't implement the Java memory model. So you can't implement some of the programming languages as defined on top of it. So the example here illustrates why this might be an issue. This is by now semi-famous example here, I guess, referred to as the IRIW, independent reads of independent writes example. So the idea here is, this looks kind of complicated at first glance, but what's going on here is threads 1 and 2 just are independent writes to different shared variables. And thread 3 and 4 read them in opposite order and convince themselves that the other one is set first. So thread 3 reads things in such a way as to prove conclusively that X was set first, and thread 4 reads things in such a way to prove conclusively that Y was set first. The question is, can this happen? The problem is that it's not complete. It's intuitively not at all clear that just by inserting fence instructions here in the middle between the two loads of threads 3 and thread 4, that as a result we preclude this sort of outcome. because one could still intuitively think of a machine where thread 1 and thread 3 are somehow located close together. For example, they're threads on the same processor core. And thread 2 and thread 4 are located close together, so they can each see each other's writes first. And just inserting a fence there that prevents those loads from being reordered in some sense doesn't change much of anything. Yet this program is fully fenced. We have fences between every pair of instructions, so it's not clear that we can do any more either. Okay. Going on here, the good news is that this has actually gotten significantly better recently. If we look at the status now, as I mentioned earlier, Intel and AMD, in fact, published much better descriptions of the memory model of those processors, which clarify a lot of those issues. So in particular, if we look back at the example on the preceding slide, the IRIW example, it actually turns out that on x86, we can get sequential consistency for that example. On the other hand, somewhat surprisingly, which I think nobody knew before the specs came out, is that this actually requires that you implement the stores in the first 2 threads into x and y using an exchange instruction. So actually, the good news is that we have a solution. The bad news is that I suspect we still have a bunch of JVMs out there that, in fact, are technically broken and don't follow the rules because they didn't know what the rules were at the time at which they were written. In general, on other architectures, similar things are happening, and we seem to have fairly good stories pretty much everywhere, as far as I can tell. We either have fairly good stories, or we've convinced the vendors that they have to do something about it. So. Okay, moving up a level in the stack here to languages and compilers. The programming rules, I will claim, the programming rules for dealing with threads in general have been pretty unclear. It's in some languages more so than others. Probably the language that's sort of in the best shape here is Java. The Java memory model, which defines basically the semantics of shared variables in Java, was fixed in 2005. It turns out there's some ongoing discussions about some of these issues here. And in fact, the issue that I just talked about implementability on various architectures was one of those that came up since then. So things haven't completely settled, but there is a mostly consistent story there. If we look at .NET and OpenMP, I think my personal opinion is that there's a lot of clarification that could be used there. For the rest of this talk, I'll actually, as I hinted not too inconspicuously in the title here, I'll focus mostly on C and C++, where the assumption so far has been, since these languages don't explicitly talk about threads, that I'm programming with the base language plus a thread library. Generally, for my purposes, pthreads, because that sort of that's backed by a standard specification. So let's look at the C and C++ with threads programming rules. The general rule, I think, probably everywhere, though certainly that's the case now. In the past, it was not completely clear on Windows platforms, I think. But in general, the rule is that we disallow simultaneous access to shared variables, what's commonly referred to as a data race. So we don't get to access the same variable from 2 threads simultaneously if at least one of them is a write. That's, for example, the rule if you look at the POSIX standard. Unfortunately, many people who program with threads and C++ don't look at the POSIX standard. So, but it's fairly clear that that was intended to be the rule. This actually is a rule that goes back fairly far. It was basically what was prescribed in the 883 standard. It was explored in Sarita Adve's thesis after that. It turns out that this solves a whole bunch of problems by just insisting that programmers not have data races in their program. Basically, you can't tell whether a lot of nasty stuff is going on under the covers. So you can't tell, for example, whether your compiler reorders loads and stores underneath because any program that would be able to detect whether two stores were reordered, for example, would have to read those essentially at the same time without synchronization. So any program that does that would have some execution where the loads and the stores occur simultaneously, so it would have a data race. So basically, it gives the implementation license to cheat without getting caught. So this applies not only to compiler reordering, it also applies to the sort of hardware reordering that I talked about at the beginning. So if now the hardware is allowed to delay store instructions by storing to a write buffer because you can't tell. Any code that can tell is wrong by definition. It also has the interesting consequence, and which simplifies the compiler writer's job significantly, is that the C or C++ compiler may in fact rely on the assumption that variables don't change out, don't asynchronously change out from underneath it. This, in fact, potentially has some fairly profound consequences, which I think a lot of people don't appreciate, though it seems to rarely encounter, these seem to rarely occur in practice, which is a common issue here. So here's an example of the kind of assumptions that a compiler is currently allowed to make, and what can happen if that assumption, in fact, turns out to be false. So we assume we have some unsigned integer variable x, and then we check that x is less than 3. And then after doing some other stuff that doesn't touch x, we execute a switch statement on x. Let's assume that that switch statement is implemented by indexing into a branch table and branching indirectly to one of 3 locations, depending on which case we're in. Since we previously checked that x is either 0, 1, or 2, the compiler is allowed to elide the range check on the indirect branch to the branch table and just assume that that's within range. And that works so long as we follow the rules. Now, what happens if, in fact, somebody doesn't follow the rules and asynchronously changes x between the conditional and the switch statement? Well, what happens, say x is changed to 5 there by some other thread in the middle. What happens is that the switch statement will merely go ahead and use x to index into a branch table, indexing off the end of the branch table and branching to whatever location is there, causing some weird stuff to happen, basically causing the program to take a wild branch. So the important thing is that in this model, by introducing a data race where we weren't allowed to have one, we get something which, in fact, doesn't correspond to just reading a different value from the shared variable. We get complete nonsense at the end. And that's allowed by current standards. So what's the reality here? As far as I can tell, the common attitude is that data races, in fact, aren't so bad. And that some data races, well, in fact, there was a paper published in PLDI fairly recently about benign data races. So, I mean, clearly, in some cases, people believe that data races are okay. So, for example, the kinds of things that people commonly do is that they maintain approximate counters in ordinary shared variables by just incrementing the counter in multiple threads without any sort of locking or synchronization. And then reading the counter asynchronously. Since these are approximate counters that are only supposed to be statistically valid, the assumption is that, well, this may go wrong every once in a while because you have a race, so you might actually lose one of the updates. On the other hand, it's not so bad. Another fairly common idiom that people use is something called double-check locking. The idea here is that you lazily initialize a value and you avoid doing the expensive synchronization on every access to that variable by checking a flag that says, has this been initialized ahead of time, and only doing the synchronization if it appears to not have been initialized. It's another one of these things that mostly works. It's a fairly common idiom. On the other hand, it involves a data race. in many environments, people actually combine this with atomic operations that are somehow provided in platform-specific ways. So on Windows, there are these interlocked operations. I already mentioned on GCC has underscore sync operations, which are often used for reference counting. And these things are often combined with reading the resulting value using ordinary variable operations, using an ordinary variable reference. All of this really isn't particularly well defined at the moment, and read accesses generally appear as a data race to the compilers, so you have to worry about things like what happened on the preceding slide where you end up taking a wild branch happening. Fortunately, this doesn't happen very often in practice, so we rarely get caught by this. On the other hand, it seems fairly clearly against the rules. On the other hand, we have the problem that locks are expensive enough that you can't quite tell people just not to do this, properly synchronize your program, because especially for something like reference counting in C++, which is fairly prevalent, the cost of doing this any other way is in fact is too high. Okay, here's an interesting complication which always enters or very often enters the discussion at this point when I bring these up, and that's, well, if you share these variables and they can change asynchronously, shouldn't you just declare the variable volatile? And the answer here, unfortunately, is sort of. It depends. So if we look at the current Java definition after 2005 at least, then the answer there is fairly clearly yes. For something like double-check locking or and some other idioms, in fact, that works just fine. So in Java, if I have an initialization flag there called xinit, and I declare it volatile, and I then assign to x and set the initialization flag, that in fact guarantees that x is set before, that x is visibly set to other threads, becomes visible to other threads before xinit becomes visibly true in other threads. So if I check xinit in another thread and then read x, I'm fine. This is often implemented by putting a hardware fence instruction before the volatile store there, and there's other stuff that's required to implement this. I want to point that out explicitly because there's an interesting contrast here. In contrast, if we were programming an OpenMP, here's a quotation from the OpenMP 2.5 spec, and I think this actually is more or less unmodified in the 3.0 draft. A reference that modifies the value of an object with a volatile qualified type behaves as if there were a flush operation on that object at the next sequence point, which essentially means that in OpenMP, the implementation should insert a fence after the assignment to xinit if I declare xinit volatile here, which I haven't yet figured out why it says that. As far as I can, I've had a lot of trouble figuring out any use case in which that's actually what you wanted to say, but nonetheless, it's clearly not consistent. If we look at the C with pthread situation, the relevant quotation here, because it makes it clearer than what's actually in the standard, is a quotation from Dave Butenhoff, who's one of the people who wrote the standard there originally. Volatile provides no help whatsoever in making code thread safe. And if you read the standard fairly carefully, that's what it says. Not as clearly, but. So we have a bunch of really different situations here. So what's actually in the C++ OX working paper? Basically, again, largely thanks to Lawrence here, concurrent access to variables is allowed, but they have to be declared specially as atomic objects. So for example, you can declare a variable as having an atomic int, as being of type atomic int, and then that provides operations to concurrently access the variable safely. And for all purposes, the concurrent accesses to an atomic int are no longer viewed as a data race. That's the way this is dealt with formally. Other than that, the C++ working paper actually doesn't make much change to what's currently the official status quo. It again reaffirms that there are no benign data races in C++. So wherever you have a data, the other way to say that is wherever you have a data race, you should be using atomics. Otherwise, the behavior is undefined, and that includes taking wild branches. It's important to be explicit here that the C++ volatile qualifier, in fact, still is of no help here. So we haven't changed that either. There was a lot of discussion about changing this. It turns out it's very difficult to do because C++ volatile, in fact, has some current semantics, which would be difficult to preserve if we also used it for this purpose. So that's why the decision was made to instead invent something new, call it atomics rather than volatiles in C++, even though that introduces this unfortunate translation problem between C++ and Java, in that Java volatiles are C++ atomics, and C++ volatiles are not Java volatiles. It turns out there are, in fact, some other more technical problems here that come up. So far, we've told the programmer to not write code that includes data races. On the other hand, it turns out that compilers, in fact, sometimes introduce code that adds data races, which is rather unfortunate. There's one sort of fairly well-known case of when this happens, and that's when you're updating a small struct field. And I'll give you a detailed example of that. It turns out this can also happen in more complicated cases if clever optimizations result in speculative stores, basically. If they result in writes back to locations that weren't written in the source, the compiler will have to be careful that what it's writing back is what it thought was there before. On the other hand, in a multi-threaded application, it's not safe to do that necessarily, because by just writing back what was there before, you may be hiding an update in a different thread. Very occasionally, this actually does happen, and the annoying thing is that if you look at the current standards, it's not at all clear that this is disallowed, at least. So for the struct field update example, which is probably the one that's bitten the most people in practice, assume we have, consider the structure up there, which is sort of a particularly tricky case, which is in fact by the current working paper miscompiled by nearly every compiler. So what happens is I have a bunch of bit fields in between two character fields in a 32-bit struct, and I assign to one of the bit fields and one of the character fields simultaneously. The way that's normally compiled these days is, say, particularly on 32-bit machines, but probably also on 64-bit machines, is I copy the structure as a whole into a temporary. I implement the bit field update by updating the bit field in the temporary value, and then storing the result back to the whole structure. On the other hand, the character field update in the other thread is implemented simply as a byte store. So that's fine and uncontroversial. It's the bit field update there in thread 1 that's controversial. And as I suspect most of you already realize, this isn't going to work. So we can actually step through this here quickly. So if we look at how this can actually be executed, we copy X into a temporary. We update the C bit field in the temporary. Now we assign to the D field in the other thread. We copy the temporary back to X, and we've just overwritten the update to D. So what happens here as a result, I've lost the effect of thread 2. So as I already said, this behavior is actually something that's both allowed and fairly common. If you look at current standards, in fact, it's worse than that. This is what implementations typically do. Implementations typically run into this problem with bit fields. The standard actually allows this to happen even if I'm just writing to fields A and D in this structure. Yeah?
Suppose that X, instead of being a structure with bit fields, was, let's say, an array of ints.
Yeah.
And let's suppose thread 1 wrote to array sub 0. Thread 2 wrote to array sub 22.
Yeah.
No one would expect those to be atomic. because X is not atomic, but the rights to 0 and 22 would be. So if you don't expect that when X is an array, why would anyone ever expect it to be true in this case?
Okay. The question, if I can summarize it correctly, is why would you expect this to work because X is not declared to be atomic?
Why are we saying the sky is falling? This is a bug, right? I would never expect that to work for the same reason I would never expect the array case to work.
Okay, in fact, I'm not sure I quite understood the array example. You're asking about simultaneous updates to two array elements.
I didn't mean to blow up the talk. It's just that
yeah.
It's just that I don't.
Oh, okay. No. This is a good question. I think it's good to be clear about this. In fact, if you look at a lot of existing code, it makes assumptions along these lines. Usually, it's in the form of I have a structure and it has, say, these fields in it. And I would like to protect C and D by different locks.
So since you proposed just one rule so far, or your slide, I would propose another one. Never use bit fields. How about that? I mean, a lot of people follow that rule now.
In some applications well, actually, let me postpone that. And what we do is actually somewhere in the middle, which I think is probably, hopefully you'll agree, is a better solution. But. Okay, so here's a quick summary of what we actually say about all of this in the current working paper. So subject to the no data erases rule. And in response to that question, I should be clear that the no data erases rule applies at the level of scalar values. So you may not simultaneously access two scalar values at the same time from the different threads. So in particular, that does not automatically prevent simultaneous access from two threads to distinct fields, or distinct array elements. So subject to that rule, each update affects a memory location, which the standard defines as either a scalar value or a contiguous sequence of bit fields. The standard then defines exactly which assignments can be seen by each reference to a memory location, which is essentially what you need in order to define the semantics of shared memory here. For ordinary accesses, there has to be exactly one assignment to a particular memory location that's visible to a particular access, to a particular load. The way this is structured is if we look back at the preceding example, a reference to x.d, after completion of both of those threads in the last example, in fact, is required to see a value of 1. And because those two threads access distinct memory locations, they in fact are not defined to be involved in a data race. So as a result, the preceding implementation of bit field assignments, as I outlined it, there is incorrect. So we no longer allow that implementation.
Is this supposed to address, 32-bit values on 8-bit processors or anything like that, or is that going to go?
32-bit values on 8-bit processors, in fact, work out generally okay because of the fact that we don't allow races. So that's in fact not an issue.
Okay,
we don't. There's an issue in the implementation of atomics on such processors. For non-atomics, because we don't allow simultaneous access without some sort of synchronization between them, you can't tell whether a particular 32-bit store is implemented in 4 pieces or in 1.
Okay, thank you. Good.
So as a result of this, if we look, the preceding implementation is not okay. On the other hand, assignments to the bit fields in the middle in fact, may not occur concurrently. Those do form a data race if I have one thread assigning to bit field x.b and one to x.c. And hopefully that answers the last question. So that's sort of a compromise solution. You can still use bit fields, but they have weaker semantics than you might otherwise expect. But it only affects bit fields. It does not affect adjacent character fields. This rule actually, it turns out, has some other more subtle consequences which are of interest primarily to compiler writers. I mentioned earlier this notion of speculative stores introduced by compilers. So here's an example of a kind of optimization that abstractly you would kind of like to see in your compiler. On the other hand, it's not one that we allow anymore. So this is a simple loop that traverses a linked list and counts the number of positive elements in the linked list. It's fairly common to transform this to a loop that initially, actually I should emphasize here, count in this particular case is a global variable that might be shared between threads. It's fairly common in current compilers to optimize this to code that loads the initial value of count into a register before the beginning of the loop, then traverses the link, then executes the loop that traverses the linked list, just incrementing the register value, and then storing the register value back to the global at the end. This transformation is not technically safe with more than one thread, because if for some reason I know that I'm invoking this on a list with no positive elements, I know that the original code never touches count. So there is in fact no data race involved if I run this concurrently with another thread that does update count. On the other hand, the transformed version always stores to count. So I've introduced, the compiler potentially introduces a data race by performing this transformation. There are ways to avoid this in this example. So in this particular example, you can, if you perform the store only if the register value is non-zero, that will generally take care of the problem. Sorry, actually you have to do this a little differently. You have to count in a local variable. You have to initialize a local variable to 0, and then if you changed its value from 0, then you add it at the end. That'll work. Okay, so the consequences of this is we are losing some useful optimizations. On the other hand, it does give the programmer a much simpler and consistent story than what we've had before. It prevents some really mysterious compiler-introduced bugs, and it outlaws primarily optimizations that we can at least replace by code that's, as far as we can tell, is only slightly slower. So I don't think this is going to have a major impact on code performance. So that was sort of at the low level. Here's another interesting problem, actually, another one that Lawrence has been spending a lot of time thinking about. This one is unlike the previous one. It's C++ specific. So what's happening here is fairly commonly what I think it's fairly common to write code which at some point during its execution starts some daemon helper thread. So we have a main thread running. At some point, the helper thread here is started. And at some point, then the main thread exits. In a C++ program, when the main thread exits, various static destructors for statically allocated variables get invoked and go away. So at some point, say there's a variable down here which is used by a shared library that's referenced from the daemon thread. The shared variable that's used by this library goes away because it's destroyed. Now the problem is, in this model, the daemon thread is still running. There's nothing to prevent the daemon thread from accidentally waking up sometime after that and trying to call into that shared library, now accessing one of the static variables of the library that has already been destroyed at that point. As far as I can tell, this is a fairly common scenario in multi-threaded C++ programs, which I suspect hasn't generally been identified as a major problem because processes only crash when they're about to shut down anyway, and nobody notices that much. But nonetheless, it's not a good state of affairs. For this particular one, actually, we don't yet have what I would consider to be a complete solution. The current state of affairs in the working paper is you basically have two choices. You can either shut down all threads properly before process exit. That's not necessarily an easy thing to do because some of those threads may be waiting on I/O, and you don't have a very good mechanism for getting them to break out of the I/O wait. Or the other alternative is, and this is Lawrence's invention, there's a way to exit the process by only executing certain special cleanup actions and not destructors, not all destructors, at which point you sort of get a semi-graceful exit, which is guaranteed not to crash, however. On the other hand, some of the things that you expected to be cleaned up might not be cleaned up. Okay, another problem here. Thread libraries. Part of the story in making all of this work is that in order to prevent races in programs, we need to have synchronization operations like lock and unlock in this slide that ensure mutual exclusion and so on. And we would like them to prevent memory reorderings with respect to those synchronization operations. So if we look at this particular example here, this is basically just incrementing x inside a critical section. We certainly want to make sure that the implementation of these synchronization primitives is such that we can't just take, say, the load of x into the temp variable and somehow reorder it out of the critical section. So we want to prevent this reordering from happening either by the compiler or by the hardware. There are a couple of mechanisms that are normally used for this. We normally prevent this reordering by the compiler by neglecting to inform the compiler what lock and unlock are at all, so they look like opaque functions to the compiler. And therefore, it looks like to the compiler like lock and unlock might touch x. And therefore, you can't do this sort of movement of the memory operation because that looks to the compiler already like it might be incorrect. On the other hand, the other part of this has to be that we have to prevent the hardware from doing the equivalent of that. We normally do that by putting fence instructions into the implementation of lock and unlock. So clearly, this is disallowed. Those fence instructions are typically somewhere between fairly and very expensive, so we need to be careful that we understand exactly where they're needed. On the other hand, so far actually it's been fairly unclear what kind of reordering is actually allowed, and therefore what kind of fence instructions we allow. So if we look at Java, for example, it's fairly clear we're not allowed to move things out of the critical section as one might expect. We are allowed to move things into the critical section in both directions. If we look at the pthread standard and read it very naively, basically what it seems to say is this, that we can't move things either way. These things just prevent reordering and cost them. If we stare at that really hard and think about what it really means, you can prove that you can do this and the result is not observable. It actually turns out you can't do that. You can't move things in past the lock. And the reason is this example. And as I said, don't ever write code like this. So the idea here is that I set some variable x equals 42, and then say I'm done with accessing the variable x by acquiring a lock, which is sort of the opposite of the way things are supposed to work. I then go ahead and wait until the lock is set, which I can do by calling try-lock repeatedly. And then I claim that at this point here, it should be the case that x is 42. The problem is this should work. This is expected to work in some sense, at least with sufficiently warped mind or something. But it breaks if I reorder the assignment of x equals 42 and the lock acquisition. So that means that in this particular case, essentially, I can't move the assignment of x equals 42 into the critical section past the lock. So what do actual implementations do? Well, we looked at some open source implementations a while ago. This is, I think, fortunately, this is also probably improved. So a bunch of implementation on weakly ordered hardware, NPTL locks tended to, in fact, assume the weaker implementation here. So they, in fact, tended to allow movement of things into critical sections in both directions, but not out, which in practice is probably OK, but technically incorrect. Some of them, I think, often just because the hardware sort of gave stronger guarantees anyway, implement this where nothing moves either way. In some cases, that's stronger than required. I think on Itanium, this is probably too slow. Some of them did the right thing, and we found one interesting case that did that, which you don't want to use. I think that's been fixed. OK, C++ 0x's solution to this is slightly weird. So movement into critical section is allowed in both directions. So how do we deal with that funny example that we didn't want anybody to write? Well, we tell you that try-lock may, in fact, fail spuriously. Which turns out it makes the example that I had up there clearly incorrect. So it still behaves. I no longer have a memory consistency problem. I just have a wrong piece of code, which actually was the goal here, I claim, because as I said, this is not code that you should be writing anyway. And I know of no cases. I've been told that there are some really obscure cases where this actually interferes with legitimate code. All uses of try-lock that I've ever made continue to work under this interpretation. So together with all the other rules, the important point from this slide here is that by using this slightly weird definition, we basically allow the standard to guarantee that memory operation reordering is completely invisible to the programmer for data erase-free programs. So even if you use try-lock or whatever, you don't have to. And the bottom line is, you don't have to worry about all this reordering stuff that we've been talking about here. That's not quite true, because in fact there are some low-level library facilities that actually allow you to write really fast hand-tuned code that violates this rule. However, that's very clearly identified when you're doing that, and so long as you don't do that, you get that guarantee. So without doing that, basically, data erase-free programs behave as though the steps are just of the individual threads are just interleaved. Let me see. I have a couple more quick slides here. Libraries in general that don't deal specifically with threads. I think there's also been some missteps here. The general wisdom about locks and, for example, general-purpose container libraries, I think it's safe to say, is that if you're accessing a general-purpose container library in multi-threaded code, the client knows whether or not that container is being shared between threads, so the locking should occur in the client. This doesn't apply to things that specifically are designed for threads use. The rules may be different. If you don't do that, you get weird performance problems and possibly even deadlock. And there's a lot of experience to substantiate that at this point, I think. On the other hand, if you look at what we actually have, it's sort of mixed, in part because people were learning at the time. So the original Java collections, like vector, are synchronized implicitly and violate this rule. And on the POSIX side, in fact, we have this problem as well. There's this interesting phenomenon that if you write a simple file copy program using putc and getc in POSIX, you can try this on your favorite Linux machine. If you fork an empty thread at the beginning of this copy program, which immediately returns and does nothing, it slows down by about a factor of 10. That's because POSIX requires that putc and getc implicitly acquire and release a lock, so they're thread safe in that very strong and usually unnecessary sense. And it turns out that behavior is triggered once, on Linux at least, once you fork the initial thread. So the C++ 0x solution here is that we basically follow what's sort of the STL convention and the recent Java convention, which is that containers are do not visibly acquire locks by default. The details here still have to be determined. We're not really done with this part yet. So where does this leave us? Well, I mean, the one thing that this has taught me, at least, is that if we start out with a single-threaded language and add threads as an afterthought, that in general doesn't work all that well. I think we really do need to get the remaining problems fixed that were introduced as a result of this. it's quite likely that there actually is a better general-purpose parallel programming model, at least for certain applications. I'm not sure that there's any one that's quite as general. On the other hand, I think it's useful to be able to fix sort of the threads and locks programming model underneath, if for no other reason than that we can actually get a reasonable evaluation of the alternatives as a result. And if you look at these alternative programming models, what's generally underneath in the implementation is threads and locks anyway, so we better get that right. Okay, thank you. Any questions?
I know in Java there's this concurrent hash map.
Use the microphone.
I know in Java there's a concurrent hash map, which basically tries to put things into separate hash maps in order to improve performance when it's being accessed concurrently. Where does that fit into this idea that the client does all the locking because it doesn't have visibility into the internal implementation of the data structure?
I was trying to be fairly careful to weasel out of this, but initially, there are clearly some data structures that will need to know about threads specifically, and that's an example of that are specifically designed for multi-threaded access. So in that particular case, it's not a data structure you should ever use if you only have single-threaded access. So the idea is the interface basically is designed for concurrent access, and as a result, the implementation can take advantage of that. That certainly makes sense. I'm all in favor of providing that sort of facility in addition to the basic containers.
Earlier in the talk, you said certain kinds of race conditions are common, but failures from them are fortunately rare. And I was a little surprised to hear you use the word fortunately. I've been writing concurrency bugs for several decades now, and I'm always happy when they show up early and sad when they show up late.
I actually agree with you. I was not being entirely serious when I stated it that way.
I wonder if there are any facilities contemplated, planned, or recommended for improving the things that you didn't want to do but did anyway. Like, when I write those concurrency bugs for the 101st time, to help me find them sooner? Are there language features or processor design features or programming practices to help?
I mean, we've been thinking about this a little bit. I mean, I think it's clear that in the eventual story, he has to involve a lot of help from tools. And some of those are out there. Wherever we had a choice, in some sense, we've tried to make things a little bit easier for the tools. So the sort of absolute prohibition against data races here, in some sense, makes things a little bit easier for data race detection tools, because if it can detect that you actually have a race, you have a bug, there's no notion of a false positive in that sense. But I think that's mostly an orthogonal issue. It's an important issue, but I don't think we have any great answers there yet.
Very early on, one of your first slides said that some of the objections to threads were that they're dangerous, and I forget, threads are evil was the thing you put up there. You haven't, and particularly considering the previous question, you haven't done anything to convince me of otherwise yet. I still don't see any reason to trust anyone in this room, particularly including myself, to write threads correctly. I mean, not implement them, but to use them correctly. Is there anything going on in the C++ standards to help address that, to help us try to trust more people to use these incredibly dangerous tools?
I mean, I think there's a consensus that there is a serious problem there, and that probably most programmers should be using higher level libraries that are built on top of this. So the problem at the moment, as far as the C++ committee is concerned, is primarily one of timing. And that's that we're under a relatively short deadline, and we have to get we have hopefully enough time to get the foundations right. We unfortunately don't currently have enough time to get those things in, but everybody realizes that those are important as well.
I just wanted to address that last question too. It is true that threads are still hard to use and evil, but if you don't know what your threads mean, then it is completely and utterly impossible to write correct code, not just merely hard. So this is a really important effort to actually define what it means when a thread actually executes.
Thanks. Any other questions?
If I can get there.
Oh, okay.
Which libraries are you, or would you like to see implemented, but I obviously don't have time to implement?
We haven't invested as much effort into it as I would like. Sort of the kinds of things that have been under discussion are probably only sort of one level up and maybe not high enough. I mean, we've been looking at thread pools and sort of threads building blocks kinds of approaches. So Intel has proposed the threading building blocks library to the standards committee, and that was sort of pushed back for timing reasons. I think that's probably not high enough. I mean, there are lots of small things that need to be added as well. I mean, there's some interesting things we keep stumbling over, just like getting reference counting right is really hard. Right and nearly optimal is really hard, and that's certainly something that should be provided in a library. And there are a bunch of things like that.
Thanks.
So my question is about shared variables, and can you make them more safe by disallowing things like address taken on that, so that it is easy for analysis to catch bugs?
We haven't really been looking at disallowing things like that. I mean, certainly you're right. I mean, you can make the analysis easier by not using those features. I haven't heard much of an argument to actually disallow them in the language. I think it would be problematic to do that at this stage, but unfortunately.
It will definitely make analysis much more usable. And once
Right.
your address is on shared variables, anything can go wrong. Right?
Yeah,
It's hard to track them around. And whatever.
On the other hand, I mean, your tool can certainly detect violations of that rule, and there's nothing to prevent you from warning of violations of that rule.
Right.
So you're free to do that in any way in some sense. So I would be worried about trying to convince people to actually restrict the language in that way, because it's very hard to convince the committee to outlaw something that's in fairly widespread use, and particularly if you can work around it somehow.
It seems like the Java world has spent an awful lot of time putting things like concurrent container classes and that sort of stuff into their standard library. Do you ever see that happening for the C++ standard? And if so, how many years are we talking? Is this, 5 years, 10 years?
It's actually conceivable that this may happen in shorter time period. I'm not sure. I have probably Lawrence is sitting there, has more experience at predicting how the committee behaves. But there is an effort to put out another library technical report, which is sort of a non-binding addendum to the standard on a fairly short time scale. In fact, at some point there were discussions of possibly getting that out earlier than the actual next standard, because there are fewer bureaucratic hurdles that has to go through. So it's conceivable that it might happen even within the next 2 or 3 years, but I'm not very good at predicting these things.
Historically, the compiler development process usually involves something like write a compiler, convince yourself it's close enough to write, send it out the door, somebody finds a bug, sends in a bug report. Certainly one of the problems with concurrency-related bugs is they're very often unpredictable, and it's hard to put your finger on the bug. And I wonder if you have recommendations about things that compiler writers can do to help verify that they're following the concurrency-related rules to reduce the number of these very hard to pin down errors that the compilers are introducing.
I think that's an interesting problem. It's probably also still a research topic, unfortunately. I think some other people have been working on building infrastructures for testing concurrent programs to try to sort of increase the cross-section of these bugs. but I don't know of any good solutions. I mean, in some cases, we were trying to sort of minimize the number of possible untestable bugs. So I mean, the absolute prohibition against data races, again, is probably a good thing, because my feeling is that current compilers make the assumption that there are no asynchronous changes. And those assumptions sort of rarely and in a fairly unknown context actually impact the generated code. So even though these violating that assumption would rarely actually cause the sort of behavior that I illustrated within the switch statement, I think testing for its absence would be absolutely hopeless. But I mean, other than that, I don't have any great ideas. It's still a hard problem, I think. Okay, thank you.